Welcome back. In the last two lectures we discussed single stage vapor compression refrigeration systems. In this lecture I shall introduce multi-stage vapor compression refrigeration systems. So the specific objectives of this particular lesson are to introduce discuss limitations of single stage cycles, introduce the concepts of flash gas removal and intercooling, discuss various multi-stage multi-compression systems with flash gas removal and intercoolers, and present a steady state analysis of a typical multi-stage system. And at the end of this lesson you should be able to explain with TS and PS diagrams the limitations of single stage cycles, describe concepts of flash gas removal and intercooling and their benefits, and analyze typical multi-stage multi-compression systems for ammonia and halocarbons using steady state mass and energy balances. We have seen that single stage systems are adequate as long as the temperature difference between the evaporator and condenser is small. This difference is normally known as temperature lift. That means the temperature difference between the condenser and evaporator is known as temperature lift, and as long as the temperature lift is small, single stage systems are adequate. But there are many applications where the temperature lift can be quite high, and the temperature lift can be large either due to the requirement of very low evaporator temperatures and or due to very high condensing temperature. That means there are many applications where for a given condensing temperature you require very low evaporator temperatures. This will increase the temperature lift. There are other applications where the evaporator temperature is not so low, but the required condensing temperature is very high. This also increases the temperature lift. So for these temperature lift applications, single stage systems, we shall see now that they have many limitations. Okay. For example, on the low temperature side, let me give some examples where we can encounter very low evaporator temperatures. For example, in frozen food industries, the required temperatures can be as low as minus 40 degrees centigrade or lower. Typically you have to freeze food products, and if you are talking about quick freezing also, you require very low temperatures of the order of minus 40 or minus 50. Another very typical application where you require very low temperature are in the chemical industries, where really very low temperatures as low as minus 150 degrees centigrade or even lower are required for liquefaction of gases. So these are the two typical applications where you encounter very low evaporator temperatures. And on the high side, if you are using the refrigerant system as a heat pump for heating applications, then the required condensing temperature can be very high. The typical applications of refrigerant system in the form of heat pump could be, for example, in process heating or in the drying. So these are two typical examples where the temperature lift is very high. And in fact, in the last class we have seen that as the temperature lift increases, single stage systems become inefficient. Let me repeat this with the help of TS and PS diagrams. For example, here on a TS diagram we have shown the effect of evaporator temperature. Here condenser temperature is fixed. This is a condenser temperature which is fixed, and I am decreasing the evaporator temperature in this direction. For example, cycle 1, 2, 3, 4 is for, let us say, an evaporator temperature of T1. Okay. For this particular evaporator temperature, this is the throttling loss, and this is your superheat horn or superheat loss, and this is your compressor discharge temperature. Now if this evaporator temperature is reduced to TE2, then you can see that throttling losses have increased by this amount and superheat losses have increased by this amount, and you can also see that the discharge temperature also increases. If you reduce the temperature further, for example to TE3, you will see that the throttling losses increase some more, and again there will be more losses in the superheat side also. Okay, again you can see that there is a large increase in the compressor discharge temperatures. So as you can see that if you reduce it further, this isenthalp continues in this manner, and continuously the throttling and superheat losses increase. Let me show this in pH diagram also. For example, this is in the pH diagram, and the evaporator temperature is decreasing in this direction. It is decreasing in this direction, and you can see that when the evaporator temperature is low, when the evaporator temperature is T1, this is T1, this is your refrigeration effect. Okay, this is our refrigeration effect, and this is the work of compression. Okay. So, when the evaporator temperature decreases, let us say to E3, you can see that the refrigeration effect reduces, and what is more important is your work of compression increases considerably. Okay. This happens because the isentropic lines, they become gradually flatter as you move away from the vapor saturated vapor curve. You can see that this pressure line is much flatter compared to this one, which is flatter compared to this. So, as they become flatter, you can see that the work of compression increases. So, you can see that as you are reducing the evaporator temperature, refrigeration effect is reducing and work of compression is increasing. In addition to that, you can also see that since the pressures are reducing, the specific volume at this point, that increases gradually. So, what is the conclusion? So, the conclusion is for a given condensing temperature, as the evaporator temperature decreases, throttling and superheat losses increase, compressor exit temperature increases, amount of vapor at evaporator inlet increases. You might have noticed it from the PS diagram and TS diagram that the amount of vapor or the quality of vapor at evaporator inlet temperature increases as your evaporator temperature is reduced, and specific volume at compressor inlet increases. So, these are the negative effects of operating the system at very low evaporator temperatures. As a consequence of all this, you find that the COP of the system reduces considerably, and the refrigeration capacity also reduces, and the life of compressor decreases rapidly. Why does the life of compressor decrease? Because your compressor discharge temperature increases, so the lubrication becomes ineffective. That means the lubrication has to operate at very high temperature. So, this makes the lubrication ineffective. So, there will be more wear and tear. So, as a result, the compressor life reduces. So, these are the bad effects of operating a compression system at very high temperature lift or at very low evaporator temperatures. And performance also degrades as condenser temperature increases. That means if you are keeping the evaporator temperature constant and increasing the condenser temperature, you will find that performance is again decreasing. So, the summary is that single stage systems are not recommended when evaporator temperature becomes very low and or condenser temperature becomes very high. In fact, they become economically unviable when the temperature lift exceeds certain limit. In such cases, we have to use what is known as multi-stage systems. Generally, a single stage system is used up to an evaporator temperature of minus 30 degrees centigrade. This is a general industrial practice. So, as long as your evaporator temperature is above minus 30, single stage system is alright. And a two stage system is used between minus 30 to minus 60 degrees centigrade. And a three stage system is used when the temperatures fall below minus 60 degrees centigrade. And multi-stage systems are also used in applications requiring refrigeration at different temperatures. That means we use multi-stage systems when the temperature lift is very high. And another application of multi-stage system is when we require refrigeration at different temperatures. So, let me give an example of it. Okay, in applications requiring refrigeration at different temperatures. For example, I give a typical application in a dairy plant. Refrigeration is required at minus 30 degrees centigrade for making ice cream and at 2 degrees centigrade for chilling milk. That means you require refrigeration effect at minus 30 degrees centigrade so that you can produce ice cream. And at the same time, in the same dairy plant, you also require refrigeration at 2 degrees centigrade for chilling of milk. Okay, so what are the options available? There are several options. For example, you can have two independent refrigeration systems where one refrigeration system will be catering to minus 30 degrees centigrade evaporator temperature producing ice cream, and the other refrigeration system will be cooling the milk at 2 degrees centigrade. This is one option. The other option is you can use a single refrigeration system where the evaporator is operated at minus 30 degrees centigrade, even though you really do not require minus 30 degrees centigrade for chilling the milk. Okay. And we shall see that this is very inefficient because you require cooling at 2 degrees centigrade, but still you are operating evaporator at minus 30 degrees centigrade. This is inefficient from the performance point of view. It can also create problems like frosting, etc. Okay, but this is another option. The third option is to go for multi-stage systems where you have multi-evaporators. That means one evaporator will be working at minus 30 degrees centigrade and the other evaporator will be working at plus 2 degrees centigrade. So this is known as a multi-evaporator system. This also comes under multi-stage systems, because you shall see that on the low pressure side you have two low pressures, one is corresponding to minus 30 degrees and the other one corresponds to plus 2 degrees centigrade. Okay, so this is a typical application of multi-evaporator system. Of course, another example is your domestic refrigerator. In domestic refrigerator also your freezer compartment has to be kept at minus 18, minus 20 like that, whereas your refrigerator compartment has got to be kept at about 0 to 5 degrees centigrade. Okay, so normally in all the refrigerators we have a single evaporator. Since you require minus 18 in freezer, you have to operate the evaporator at about minus 25 or so that freezer temperature can be achieved. So for a large part in the refrigerator, even though your required temperature is 5 degrees centigrade, you are still using the same evaporator which is operating at minus 30 or minus 25 degrees centigrade. Okay, so this is actually thermodynamically it is inefficient and it leads to large irreversibility. But unfortunately in domestic refrigerators the use of multi-evaporator system is generally not justified from economics point of view, because you will see that in a typical multi-stage system you will be adding more components, so cost will be increasing. Okay, so multi-evaporator system or multi-stage system is economically justified when the system capacity is large and the benefits in power savings overcome the initial cost, whereas in typical domestic refrigerator system this may not be the case. Okay, but still thermodynamically that is another example where you can use a multi-evaporator system. Okay, so as I was saying, instead of using a single evaporator or two different systems, we can use a multi-evaporator system with low temperature evaporator operating at minus 30 degrees and the high temperature evaporator operating at 2 degrees centigrade. Okay. So how do we define a multi-stage system? A multi-stage system is a refrigeration system with two or more low side pressures. So in general it can be anything, it can be a 2 stage, 3 stage or more. Okay, it will have a single high pressure, but there will be more than one low pressures. Multi-stage systems can be classified into multi-compression systems, multi-evaporator systems, cascade systems, etc. Two concepts which are normally integral to any multi-pressure systems are what is known as flash gas removal and intercooling. So let us discuss these concepts first, then let us move on to the systems. So first let us look at flash gas removal. What is flash gas? Flash gas is the vapor formed during throttling of refrigerant liquid in expansion device. While discussing methods of producing refrigeration, we have seen that when you are expanding a saturated or a slightly subcooled liquid in such a way that some liquid flashes into vapor, you can produce very low temperatures. So this is actually the working principle of vapor compression systems, where you attain very low temperatures by flashing some of the liquid into vapor. Okay, so flash gas generation is required to attain low temperatures, and the job of the flash gas is done once the low temperatures are achieved. Okay, so what is the problem afterwards? Afterwards the problem is the flash gas has got to be compressed back to the condenser pressure, and it does not really contribute to the refrigeration effect as it is already a vapor. That means it has already done its duty by reducing the temperature, so it cannot contribute any more to the refrigeration effect. So there is no point really in sending the flash gas through the evaporator, because it cannot take any more heat. Okay, because the refrigeration effect in the evaporator is due to the latent change. Okay, and since it is already in the vapor form, it cannot undergo any more change. Okay. And another disadvantage is that it increases the pressure drop in the evaporator. Okay, so these are the problems. Once flash gas has reduced the temperature, you see that it has to be compressed back and it does not contribute to refrigeration effect, and it increases the pressure drop in the evaporator. So flash gas removal. Performance can be improved considerably if the flash gas is removed as soon as it is formed and recompressed to condenser pressure. That means, let us say that you have found a way by which you are continuously removing the flash gas as soon as it is formed in the throttling device, and you are compressing it back to the condenser pressure. That will give you the best performance. Okay, because you are not allowing the flash gas to go to the evaporator. As a result, evaporator will be operating efficiently. Okay, but unfortunately this is not possible in practice. the continuous removal of flash gas as soon as it is formed and recompressing it immediately is very difficult in practice, and so far no practical means to achieve this could be found. So what is the practical way of at least reducing the damage? So a practical way is to remove the flash gas at an intermediate pressure is by using what is known as a flash tank. So let me explain what is a flash tank. So a flash tank is a pressure vessel in which the refrigerant liquid and vapor are separated at an intermediate pressure. So it's basically a pressure vessel where liquid and vapor are separated, and this operates at a pressure intermediate between the evaporator and condenser. Refrigerant from condenser is first expanded to an intermediate flash tank pressure using a low side float valve. That means use a float valve to reduce the pressure from the condenser pressure to an intermediate pressure corresponding to that of flash tank. The float valve maintains a constant liquid level in the flash tank. Refrigerant liquid and vapor are separated in the flash tank, and saturated liquid from flash tank is fed to the evaporator after throttling it to the required evaporator pressure. So this is the description of a flash tank. Let me show it schematic of a flash tank. Okay, so this picture here shows the a typical flash tank. What we have here is high pressure refrigerant from the condenser. First flows through a float valve. Okay, float valve is an expansion device where the pressure drops from the condenser pressure PC to an intermediate pressure corresponding to the flash tank, that is PI. Okay, so pressure drop from PC to PI takes place across the float valve. Okay, PC to PI takes place across the float valve, and the flash tank is maintained at a intermediate pressure PI. And in the flash tank, what is done is, you can see that only the refrigerant liquid is taken to the evaporator through the expansion valve. Okay, that means you separate the, here what happens is see at this point you have both liquid plus vapor. Okay, because of this is as a result of the flashing that has taken place in the float valve. So what we are doing here is we are sending the vapor to the compressor or to a reduction valve, and we are sending the liquid portion to the evaporator through an expansion valve. What does this expansion valve does? This reduces the pressure from PI to PE. PE is your required evaporator pressure. Okay, so this is the description of a typical flash tank. Normally you may have to insulate this if this temperature is lower than the surroundings. Okay, and typically this kind of a float valve is known as a low side float valve because it maintains the liquid level on the low pressure side. Okay, one important requirement here is that the vapor that is going out of the flash tank should not carry any liquid. That means this has to be only pure vapor. It cannot be liquid plus vapor. Okay, so to ensure that, what you have to do is you have to maintain the upward velocity of the gas or upward velocity of the vapor less than certain value. Okay, typically it is seen that if the velocity of the vapor at this point is less than about 1 meter per second, then the vapor cannot carry any liquid droplet. So what you have here is pure vapor. Okay, so you have to design the flash tank in such a way that you get a low temperature here. Okay, now let me show this process on pH diagram. So this is the process on the pH diagram. This is the inlet. This is your inlet to the float valve. It is entering at 0.6 in the float valve, and in the float valve the pressure has reduced from PC to PI. Okay, so this is the operation of the float valve, and this is the point at which the refrigerant enters into the flash tank. So you can see that at this point it consists of this much fraction of vapor and this much fraction of liquid. So what you are doing is you are taking the liquid fraction which exists at this point to the evaporator through another expansion valve. This is the expansion valve. Okay, between the flash tank and the evaporator. Okay, so the saturated liquid goes to the evaporator, and the vapor that has formed at this point goes to either a compressor depending upon the system, or it may be reduced in pressure and again mixed with the low pressure evaporator gas. Okay, so one thing you can see is that if you don't have this flash tank and all, the quality at the entry to the evaporator would have been 9-. Okay, by using the flash tank you could reduce the quality considerably. So you can see that at the inlet to the evaporator 0.9 has more liquid than vapor compared to 0.9-. Okay, so this is the briefly the working principle of a flash tank. Now let us look at intercooling, the other concept of intercooling. the specific work input to a compressor in a reversible polytropic compression is given by this expression. Okay, this expression basically is obtained by integrating this, and all polytropic process, if you remember, follow this equation. PV to the power of n is constant. Okay,